Good afternoon, everyone. My name is Bokduk Jung, and I'm from Samsung Research. Before we begin, thank you for staying with us through the final session of the conference. Today, I'm excited to introduce Islet, our open source project that focuses on on-device confidential computing for secure and privacy-first AI. Let's explore how this technology helps protect data and maintain privacy in AI applications. Let's quickly go over what we'll cover today. First, we'll discuss the privacy concerns surrounding the rapid growth of AI. Then, we'll dive into how confidential computing offers a solution for advancing AI safely. And finally, I'll introduce Islet, our on-device confidential computing solution that brings these ideas to life. Let's get started. Progress in AI brings exciting new opportunities to every aspect of our lives, ranging from productivity tools for predictive analytics and chatbots to creative tools for generating images and videos. But as promising as this technology is, there's a dilemma. AI involves large amounts of personal data, which increases the risk of data breaches and privacy violations. And this isn't just a hypothetical concern. We've already seen it happen. For instance, Samsung banned employees from using ChatGPT over fears that sensitive corporate data could be leaked. Elon Musk also expressed the concerns when Apple integrated OpenAI into its OS, questioning how user data would be managed. Even Microsoft delayed the release of its new AI feature, Windows Recall, due to security flaws. Let's now break down the privacy risk from those examples. In the first case, training AI models from sensitive data leads to models unintentionally generating content that includes private information, which can be exposed to others through user queries. Another risk is the learning from prompts, where AI systems could retain sensitive inputs and use them for further training, increasing the likelihood of exposure. In the second case, the issues of cross-platform data leakage come into play. This happens when personal data is transferred between platforms without consent and is misused, for example, for model training. Finally, the third case demonstrates the threat of data breaches caused by hacking. These risks all require careful attention and robust solutions to ensure data privacy and security. As a potential solution to privacy concerns, deploying AI services on-premise or on-device may seem like a good approach. This approach gives data owners more control and reduces the chance of exposure. However, this introduces a new challenge for AI model providers. While some AI models are open source, many are kept proprietary to protect intellectual property. Without proper safeguards, these proprietary models could be exposed, leading to financial losses. If malicious users gain access, they could extract the model or even reverse engineer it through extensive queries. So, it's not just the user data that needs protection. AI models themselves must also be safeguarded. To address privacy concerns, we've seen several strategies beyond just making the AI models privacy-friendly. These include techniques focused on directly protecting the data itself, ensuring transparency and accountability through the regulatory compliance and access control, and lastly, enhancing security at the computing stage with algorithmic security technologies. However, these data protection techniques like de-identification and differential privacy often come with downsides. While these methods aim to protect privacy, they can reduce data accuracy or lower overall data quality, making it harder to retain full utility in AI applications. Techniques like homomorphic encryption and multi-party computation show promise, but face significant challenges. While they preserve privacy, they often suffer from performance slowdowns and are mostly limited to use by experts in specialized cases. These technologies are still developing and are not yet practical for large-scale, real-time AI use. So here's where confidential computing comes in as a solution. Confidential computing addresses both privacy concerns and the need to protect AI models. It ensures that neither data quality nor performance is compromised, offering a balanced and scalable approach to secure AI development. Now, let me introduce what confidential computing is and how it can be applied to protect both AI models and user data. Confidential computing is a security and privacy-enhancing computational technique, especially focused on protecting data in use. Data exists in 3 states: at rest, in transit, or in use. Today, encryption is commonly applied to data at rest, like in storage systems through Linux's dmcrypt, or in transit, using secure protocols like HTTPS and TLS. However, data in use, when loaded into memory, often remains unprotected. And that's where confidential computing comes into play. Protecting data in use is achieved through trustworthy hardware. Trustworthy hardware refers to secure areas of the main processor, known as trusted execution environments, where computation takes place. In addition, it includes memory encryption. There are 2 key primitives that make confidential computing work. The first is strong isolation through hardware-backed TEE. As shown in the diagram, the blue box with the orange border represents secure code and data within a TEE. Depending on the hardware architecture, this environment could be an enclave for part of the application on the left or a full virtual machine on the right. The key idea is that no one except the blue execution area itself can access it. This applies even to highly privileged firmware, hypervisors, or the operating system. This makes it highly resistant to physical threats, such as supply chain attacks or insider threats. Before we provision any sensitive code or data into the blue execution area, we first need to confirm that the blue box is truly running in a confidential computing environment. This must be verified in a way that anyone can check independently and always get the same results, showing that the blue box is protected by the TEE. This is where the second primitive, attestation, comes in. Attestation proves and verifies the integrity and authenticity of both the hardware TEE and the software running within it by using cryptographically signed proofs. Let me walk you through how attestation works using a simplified diagram. First, the code running inside the blue box requests an attestation report from the hardware. Next, the TEE generates this report. which includes evidence that hardware TEE is being used and a hash of the code and data inside the secure area, proving the integrity of the confidential VM. This report is then signed with a cryptographic signature. Finally, the signed report is sent to a remote verification service, which checks its validity. I think it doesn't work. Moving to next slide. I cannot move to next slide. Thank you. Now that we've covered the two key elements of confidential computing, let's explore how we can mitigate the risk we discussed earlier and drive safe AI progress. As shown in the diagram, by integrating confidential computing throughout the entire AI pipeline, from creating a model and provisioning it to the AI service host, and transmitting private data from user device and processing it at the AI service host, we can achieve complete confidentiality. This end-to-end approach ensures that AI operations are shielded from external threats, preventing data breaches from hacking or model leaks. Furthermore, by leveraging confidential computing to further restrict AI operations to memory and block unauthorized data transfers to external systems, internal misuse of data, such as learning from prompts or cross-platform data leakage, can be prevented. For on-device AI, running AI within CC environment secures AI models on the user's device, while preserving the advantages of local processing, such as greater control and instant responses. Additionally, CC ensures secure inputs, like voice data. It also supports secure messaging, enabling direct end-to-end encryption, and it ensures that the keys are known only to the involved parties, without the risk of external exposure. It's not just limited to AI. Confidential computing has the potential to boost privacy protection everywhere across industries. It drives privacy innovation in personalized applications like online ads, as well as in other fields dealing with sensitive information, such as blockchain, fintech, and healthcare. Confidential computing has primarily been adopted in the cloud, with x86-based architecture like AMD and Intel leading the way. In 2021, ARM also introduced support for confidential computing, targeting both servers and edge devices. Bringing ARM's confidential compute architecture to user devices like laptops and smartphones enhances app privacy by securing user-generated data. This could also benefit device OEMs like Samsung by allowing them to enhance the security of their own code, data, and AI models. For example, Samsung services like Galaxy AI and Wallet could leverage this technology in the future to keep sensitive data, even from Samsung. It could also improve security for Samsung's apps, which track sensitive user data, including daily activities. Lastly, it creates opportunities for new features. For instance, Samsung could offer a CC-based secure I/O service to ensure the authenticity of inputs, like camera, phone calls, or GPS locations. This input source attestation adds an extra layer of trust to how data is collected. At Samsung Research, we are preparing for these emerging opportunities by developing software that enables confidential computing on ARM devices and we are making this project open to the public. Alongside this, Samsung is a member of the Linux Foundation's Confidential Computing Consortium, and our open source Islet is now part of the CCC's initiative. In a nutshell, Islet is a confidential computing platform software designed with security in mind for end-user devices. Islet provides a confidential computing platform with two main components: Islet Realm Management Monitor and Islet Hardware-Enforced Security. Islet RMM manages confidential VMs, also called realms, on application processor cores. Islet HES operates separately and handles security tasks like attestation and realm key management. Since CCA has only been released as a specification in public, Islet currently runs on the simulator provided by ARM. Islet fully complies with ARM's RMM specifications and integrates seamlessly into the ARM ecosystem. It supports Linux, including KVM patches for ARM CCA. This allows for seamless deployment and compatibility with existing infrastructure. Islet is transforming on-device security by moving beyond traditional software models, offering a comprehensive confidential computing platform. It's written in Rust, a language known for its strong memory safety. We also handle the need for unsafe code in system software by encapsulating it within safe abstractions, increasing overall security. Additionally, we perform formal verification to further strengthen security, with a particular focus on RMM attack surfaces. We take a practical approach to verification, incorporating model checking techniques to automate the process. While confidential computing protects data and code from external threats, it doesn't prevent apps from misusing data. To counter this, our architecture is designed for transparent verification of app data usage, ensuring compliance through the platform itself. Lastly, Islet is for end-user devices. It aims to provide a secure environment for third-party apps. This marks a significant shift from traditional models where only OEM-authorized apps, like those using TrustZone, could run securely. We're exploring the benefits of confidential computing on everyday devices and implementing use case scenarios in gaming and AI. Unlike server-based solutions, on-device confidential computing requires lightweight, efficient methods. Our current focus is on making app provisioning and execution more efficient and developing secure communication channels between confidential VMs, which is vital for mobile environments where apps interact frequently. Beyond that, we are continuing to improve platform security and explore more mobile-specific features to accelerate the adoption of confidential computing. To wrap up, confidential computing is a new initiative for safe progress in AI, addressing both privacy and AI model protection without lowering data quality or degrading performance. On-device confidential computing opens up new opportunities to device OEMs like Samsung, as well as third-party app developers. Lastly, Islet is an open-source project aiming to enable confidential computing at user devices using ARM's new architecture, CCA. Islet aims to lead a new era of secure computing, not just for Samsung devices, but for all end-user devices. As an open-source initiative, we invite your participation in building the secure devices of the future. Here is the Islet URL once again. Thank you.